Hello everyone, myself Professor Nirmala Kumari of ENTC Department, KKY Institute of Engineering Education and Research. I am going to discuss here about fundamentals of HDL, which is a third year electronics subject of Savitribai Phule Pune University. I am going to discuss here about Unit 1, which is Introduction to HDL. The contents which are there in this particular unit are Introduction, why HDL, a brief history of HDL, structure of HDL module, operators, data types, types of description, simulation synthesis, brief comparison of VHDL and Verilog. I am not going to discuss all these in this single video. You can watch more videos, my videos for all the contents to be covered. But here in this particular video, I am going to discuss only few things. Let's see what are they. First, let me ask you, what is HDL? Can anyone answer? Just think of what is HDL. Let us see. HDL is any language from a class of computer languages, specification languages, modeling languages. So you can say now HDL is any language from computer language, specification language or modeling languages. It is a textual description consisting of expressions, statements and control structures of the spatial and temporal structure and behavior of electronic systems. It is also a form of formal description and design of an electronic circuit and digital logic. So HDL is just a formal description. And HDL allows for the automated analysis, simulation and simulated testing of an electronic circuit. So this is one of the feature that we can say that it allows for automated analysis. So analysis will become easy because automatically it will get over with the help of simulation and synthesis. And simulation is nothing but testing, verification of your functionality. So now what is the purpose of HDL? The purpose of HDL is to get both done, that is simulation and synthesis. Now in short, if I say simulation is converting your HDL description into test bench waveform or verified output, that is verifying the functionality of the design, whereas synthesis is converting your HDL or textual description into a list of components where that will be implemented on a given PLD. Let's see what is the simulation. As I said, the simulation output will be similar to this timing diagram what you are watching here. For any function, let me say some function which is given A, B, C and output is Y. So for different inputs like 0, 0, 0, my output Y is going to be 1. And 0, 0, 1, my output Y is going to be 0. 0, 1, 0, my output Y is going to be 0 again. 0, 1, 1, my output Y is going to be 0 again. So from this output you can easily say what the functionality it is and you can verify. Suppose if it is NOR gate, what is the output of NOR gate? Only when all the inputs are 0, output is 1. For remaining all other inputs, output is 0. This is how you can verify and say yes, my output is correct. So simulation is used to writing a model for the expected behavior of the circuit before that circuit is designed and built. We are not really on the hardware going to build up the circuit. We don't build it, but as if we are going to make out the hardware circuitry, as if we are going to build it and test it. So that model will be prepared with the help of again the software. So that is what is called as simulation. So simulation is used to write a model. Writing a model, I mean to say, here we are writing the program for the expected behavior of the circuit before that circuit is designed and built. And then the model is fed into a computer program called a simulator, which allows the designer to verify that the solution behaves correctly. So here just the example which I told you, that it is working as a NOR, and we said yes, fine, for the NOR we want these particular outputs. For 0 0 0 it should be 1, and remaining others the output should be 0. And from this diagram we can say, see, watch and see and verify, yes, it is working perfectly. So this process of doing all this, verifying the functionality before actual implementation of the hardware with the help of the software modeling, is what is process known as hardware simulation. Next is the synthesis. Synthesis is used to write a detailed description of a circuit that is input into another computer program called a logic compiler. So writing the detailed description of a circuit into another computer called as logic compiler. So now the compiler does your compilation, and the output of that compiler is used to configure a PLD like FPGA or CPLD, so that that PLD will perform the hardware function. Actual hardware functionality will be seen on the given PLD. So in short I can say, it is again the description, that hardware description language converting into a netlist. So here you can see it is the list of the components. So the software tool itself will, the synthesizer will generate you netlist in this format. So it is showing you 2 AND gates and a OR gate. Are these 2 AND gates? This is NAND and OR gate. And similarly here, after that netlist, simply like to show simple synthesis model. A and B are given and it is producing some Y by doing some addition. But in detail, what is this adder? This adder could be some, or adder or whatever function it is, could be something which is structured and connected like this with the help of the logic gates. So now the synthesis tool or the synthesizer will give you these list of components, that it needs 2 AND gates or 1 AND gate or 1 OR gate, or whatever based on your logic function, or whatever based on your design. That many things will be produced by the synthesizer. So it converts your description into a list of components. For that process is what is called as hardware synthesis. Now what are the uses of HDL? First use of HDL is to write executable specifications for hardware, and next use to model a piece of hardware before it is created physically. As just now I said, before actual implementation of the hardware, we are doing it on the PLD. That means our HDL now it is used to write a model a piece of hardware before it is actually created. And the other use is, it is this executability that gives HDLs the illusion of being programming languages, and they are more precisely classified as specification languages or modeling languages. Simulators are capable of supporting discrete events. That means, I mean to say, simulators are capable of supporting the digital data and also analog data, that is continuous time, and HDLs are targeted for each are available. Suppose I am modeling only a digital device, then that also can be done with the simulator. If I am modeling analog device, that also is possible with the simulator by writing in that fashion the hardware description language. So using the HDL, we can model both the digital as well as the analog models, and we can even make use of the simulator which supports these two. Now what are the different levels of abstraction that we call it as the modeling styles for writing a HDL? So let's see one by one. First is the architecture or algorithm level. which describes the functionality or behavior of a circuit, just describing the internal behavior of a circuit. Next is the register transfer logic language, that in short we call it as RTL, which describes the data flow of a circuit, flow of the just data, how the data is flowing from input to output is just described as the data flow in RTL level. And in the gate level, describe the connectivity, in short it is structure of a circuit. And next one, switch level, the MOSFETs as a switches are considered, like MOSFET on switch and off switch are considered, and if these MOSFETs are connected in one fashion, then they also will build up your logic function. So in switch level, like MOSFET level or base level, if we describe the hardware description language is described, then that level is called as switch level. So this hardware description language, when we model it, that means when we are writing the code or when we are writing the program, you can write in the behavioral modeling, that is complete behavior, or just as a flow of input data to output, that is RTL, or gate level, that means interconnection of components is what is the gate level. That level also we can describe or we can write the code. And lastly, the base level or the last level is the switch level using the MOSFETs. If we describe the behavior, then that is called as the switch level. So these are the different levels of abstraction, but basically the first three are considered, that is the behavioral modeling, data flow modeling and structural modeling are the main or basic three levels of abstraction which are widely used. Anyways, switch level, and we sometimes also use the mixed modeling, where in the mixed modeling our behavioral model and the data flow model might be used, or behavioral model and structural model might be used, or data flow model and gate level model also can be used. So some of these models can be mixed up and done as mixed modeling, and sometimes we even can use mixed language. When I say mixed language, there are some languages which I'll tell you in the next slide, where we can mix up these languages and also can describe the design or describe the functionality, that we call it as the mixed language. But overall, there are basically three levels or three abstraction levels: behavioral, data flow and structural level. Now let's move on to the design flow of using HDL. First, we need to think of what we are supposed to design. So what we think of what we are supposed to design is what is called as idea, and that idea, if we are putting in the format of HDL, that is the hardware description language, or writing the code, is what is the behavioral model. Here I have taken the language as Verilog, so Verilog behavioral model you can see, and this Verilog behavioral model has to be verified. How do you verify? Verifying is nothing but verifying the functionality of the design, is what is simulation that we have seen in the previous slide. So that is done in the next step is Verilog Excel verification, and then the synthesis is done. The synthesis tool is named as Synopsys. Synopsys is the tool which is used for synthesis purpose, that is the logic synthesis. What is synthesis again? Converting your program into a netlist. And you are again verifying here the structure of this, because when it gives you a list of components, it is nothing but the group of components which are connected together to make up your circuit. So that we call it as the structural model, and then you verify it. Once you verify it, then that is again post synthesis we do it, post simulation we do it, and here the back arrows what you see here are, if at all you are not satisfying with the verification results or the output results, you can go back and make changes so as to get your desired output. And in fact, some of the cell libraries which are needed for verification in the physical design are used. Physical design, when I say, it is really actual implementation on the hardware. So that it will be the last step in the front-end design flow. So these are the basic steps. First is taking your idea, writing the program, then simulation, then synthesis, and verifying and checking out your results. If needed, you go on to physical design, is what is the flow of using HDL. Now, why to use the HDL that we are supposed to see? The use of HDL is difficult to design directly on the hardware. As I said, you design, you make out equations, you solve it, you will try to get the values of the components, like resistor should be of this value, this should be of this value, and you may need to have a register of this size and so on. You may make it out. But if you are directly going onto the hardware and if you don't find the results to be correct, then you are supposed to replace all the components. So that becomes again a difficult. So this can be done on the software platform with the help of the hardware description language, where you can implement on the PLD, you can make changes, you can correct it, and then you can actually real time you can implement on the hardware once you are satisfied with the results. So the use of HDL is why we go for it, because it is difficult to design on the hardware. And mixed level modeling and simulation is also possible. As I said, mixed level is combining data flow and behavioral, or combining data flow and structural. So that is possible, and simulation is also possible with the hardware description language. So that's why we go with HDL. And it is easier to explore different design options, like designing methodology can be any, and you can do it in any of the ways. You can explore and implement with the help of HDL. And reduce design time and cost is one more thing why we go for HDL. And these days it would be impossible to design a complex system on a chip for a mobile device or any other consumer electronic product without an HDL. You cannot see. It is highly impossible. That's why most of them now go for the HDL other than the other programming languages. Now, what are the types of HDL? There are three basic types of HDL. They are VHDL, Verilog, and System Verilog. VHDL and Verilog are considered general purpose digital design languages, whereas System Verilog represents an enhanced version of Verilog. Each has its own style and characteristics. VHDL has roots in the ADA programming language in both concept and syntax, while Verilog's roots can be tracked back to an early HDL called Hilo and the C programming language. So, in short, I can say System Verilog is the advanced version of the Verilog, and VHDL and Verilog are mainly for general purpose digital design languages. For higher designs or for enhanced characteristics or for more complicated functions, System Verilog is used. System Verilog includes a set of extensions to the Verilog HDL, as I said just now, to help engineers design and verify larger and more complex logic designs or more complex designs. So now you can have the look at Verilog and VHDL. Verilog is similar to C, whereas VHDL is similar to ADA. Verilog is popular in commercial on coasts of US, and VHDL is popular in military Midwest US. Verilog designs contained in modules, whereas VHDL designs contained in entity architecture pair. What are these modules? What are these entity and architecture? That anyway we will be seeing in the next units, or in detail in this unit also. I'll give you some of the examples, but in detail in the actual implementation we will be looking in the coming chapters. Now you may think of, we have the C programming, we have studied very well, we have implemented so many things. with the C programming. So let's have a look at the C programming. C programming is general purpose programming language. C program can be compiled for a wide variety of computer platforms and operating system. This language has become available to a wide range of platforms and operating systems from embedded computers to supercomputers. So now you can imagine this usage is also huge, or to a large extent that we can say. But now let's see what is the difference between C programming language and hardware description language. Because till now we were discussing about the hardware description language, but you also know very well C programming is widely used. So let's see what make the difference between these two. C is a middle level language. It is a mix of high level language and an assembly language, whereas hardware description language, that is HDL, is a hardware description language. It uses for implementing the hardware circuit. C can only handle sequential instructions, but VHDL, which is one of the language of HDL, allows both sequential and concurrent executions. C program can use successfully written with pure logical and algorithmic thinking, whereas VHDL programmer needs thorough working knowledge of the hardware circuits. You can see here nowhere you are thinking about the hardware in the C programming. Whatever it is, we are not thinking about the hardware, but here we need to have thorough working knowledge of the hardware circuit. He or she should be able to predict how a given code will be implemented in hardware. Then we can use this hardware description language. We don't care about resource usage in C because C program runs on a computer which uses powerful processor with high speed. It doesn't care about resource usage. It just runs on a computer which uses powerful processor with high speed, whereas the memory and other logic elements are limited in some FPGA because we implement on a PLD. FPGA is one of the PLD, that is the programmable logic device. It is very difficult to implement image processing algorithms in VHDL, but hardware implementation again will become easy when you go with this hardware description language. So what are the advantages of HDL? Advantages compared to traditional schematic based design are so many. Some of them let's see. That is design with RTL description as well as the design with logic synthesis tool. It can be possible in the abstraction level, and it is independent of fabrication technology, and reuse when fabrication technology changing is also possible when we go with the design of anything with the RTL description or logic synthesis tool. When I say independent of fabrication technology, it is nothing but fabrication is done in the nanometer technology. Even though the nanometer technology changes, hardware description doesn't bother because it is a front end and we see only the way we verify only the results. But when we really actually go back after the synthesis, then we need to think of how much changes has to be done. So reuse when fabrication technology changing also is possible by designing with RTL description and logic synthesis tool. So this is one of the biggest advantage of HDL. As well, functional verification also can be done early before actual implementation or before going on to the hardware platform. In the early stages, the functional verification can be done early. And it is optimized to meet the desired functionality. Some of the optimizations can be done. So these are some of the advantages, and it is analogous to computer programming or similar to computer programming, like writing the textual description with comments. That all we do in the C programming and Java programming and other programming. Similarly, here also we can do it. So this is again one of the advantages of HDL. So in conclusion, we can see software programming languages and HDL are very different languages because both have many basic level differences. Even if they seem to have very few similarities, they have most of the differences. What are the differences that we have seen? And we have seen VHDL, Verilog also, and C programming and HDL also. Those differences you know very well now. And in contrast to meet most software programming languages like C, HDLs include an explicit notion of time, which is the primary attribute of hardware. So I hope you have understood what is HDL, why to go for HDL, what are the advantages of HDL, and what are the different HDLs and their comparison with the C programming languages you have seen in this particular video. So you can watch the next videos for the other topics. Thank you for watching.